Hello all. Now I'm going to discuss about the concept of stability. Next we'll discuss about the root locus. First I'm going to discuss about the concept of stability and wrote the Hurwitz's criteria. So here the term stability refers to the stable working condition of a control system. Every working system is designed to be stable. So here the stability of LTI system may be defined as when the system subjected to bounded input, the output should be bounded. So, what is bounded input, bounded output means finite input, finite output. I am having a system. For this system, I am giving finite input, bounded input, such that I have to get the bounded output, finite output. Means the system should tend to 0 as time t tends to infinity. As time t tends to infinity, the system has to reduce its amplitude. It should have the value in a decreasing manner. As time tends to infinity, I should not have a signal such that its amplitude is going on increasing. So at time t is equal to infinity, amplitude will also be infinity. So if I am having a system with output as a infinity, then the system is said to be unstable system. Okay. So here BIBO means the system should have a zero response as time t tends to infinity. So here every working system is designed to be stable. In a stable system, always the output or a response is predictable for a finite and stable input. And there are different definitions for the stability. So I'm just here writing a system is stable if it's it already we have already discussed this one, if its output is bounded or finite. For bounded input, that is finite input. And second definition for the stable system is a system is asymptotically stable if in the absence of the input the output tends towards 0 irrespective of initial conditions, irrespective of initial conditions. For asymptotically stable, if in the absence of input the output tends to 0, the system, the input is 0, the output is going to be 0, then the system is said to be asymptotically stable system. We are having stable system, unstable system, marginally stable system, and asymptotically stable system. What is stable? Bounded input, bounded output. What is asymptotically stable? If there is no input, output should be tends to 0 irrespective of initial conditions. And third one is a system is stable. A system is stable if for a bounded input the output vanishes ultimately. The output vanishes ultimately as t tends to infinity. It is same as bounded input, bounded output definition, stable system only. Next, we'll have limitedly stable system or marginally stable system. It means the system is having constant amplitude oscillations, constant amplitude oscillations. Then the system may be stable or unstable, stable or unstable under some conditions or under some limited constraints. Such a system is known as limitedly stable system or marginally stable system. Stable or marginally stable. Fifth one, if a system output is stable for all variations of its input parameters, then the system is said to be absolutely stable system. If system is the system output is stable for all variations of its parameters. Such system is called absolutely stable system. Absolutely stable system. Like this, we are having more definitions for the stable system, absolutely stable system, conditionally stable system, uh, asymptotically stable system, such that we are also having the definition for conditionally stable system. Conditionally stable system means the system output is stable for a limited range of variations of its parameters. Here there is, if there is any change and or variations in its parameters, the system is stable, means then it is known as absolutely stable system. But the system output is stable for a limited range of variations of its parameters. There is limitations in the variations of its parameters, then it is known as absolutely stable system. Sorry, conditionally stable system. Okay. So now just I am going to draw the diagrams. Means by drawing the diagrams, I just want to show what is stable, unstable, marginally stable system. Okay. So our system, I'm having f of s is equal to 1 by s plus a. Okay, this is a system I'm having whose Laplace transformation is 1 by s plus a. Okay, then pole locations, s plus a equal to 0 means s is equal to minus a. That is left half of the s plane. In the left half of the s plane, I'm having the pole, and that is located at minus a. Okay, so pole is all the poles. Here the system is having only one pole, and that one pole is residing in the left half of the s plane. Then it is known as absolutely stable system. Whatever the variations I'll do for the parameters of this system, the output is always That is, the poles are always lying on the left half of the S plane, and its impulse response 1 by S plus A, its impulse response will be e power minus at. E power minus at is nothing but it is continuously decreasing. E power minus at. Okay, it is continuously decreasing. As t tends to infinity, its response is going to be 0 somewhere around at some t values. Okay, so it is continuously decreasing and its amplitude is going on decreasing, and somewhere around at t is equal to infinity it is going to be 0. Then the system is said to be absolutely stable system. Okay, this is the first system I have considered. Second one is f of s is equals to 1 by s plus a whole square. 1 by s plus a whole square means I am having, this can be written as 1 by s plus a into s plus a, right? The system is having two poles and these two poles are lying at same position, S1 and S2, both are at minus A. Then it is also absolutely stable system and its impulse response will be like this. It is first increases, next it is decreases, and somewhere around at t is equal to infinity, its response is going to be 0. Impulse response t into e power minus at. It is also absolutely stable system. A third system I am considering. This is f of s is equals to 1 by s plus a whole square plus b square. So its impulse response will be e power minus at into sin bt. I already discussed this formula. Actually, e power minus at Laplace transformation will be equal to 1 by s plus a, and Laplace transformation of sin bt is equal to b by s square plus b square, like this. Now I am having e power minus at into sin bt. Okay, its impulse response is nothing but wherever you are having s, that it is replaced with s plus a. b by s is replaced with s plus a, like this, right? This is a given system. For this, its impulse response will be e power minus at into sin bt. Okay, now where the poles are lying? The poles are lying on imaginary axis. This is s and this is j omega plane, and the poles are lying on real and imaginary axis. Now I am having its impulse response. Sine is nothing but continuous sine signals, like this, and it is multiplied with e power minus at, like this. If these two are multiplied, then I will have the sinusoidal oscillations with decreasing amplitudes, like this. Okay, and somewhere around at t is equal to infinity, the amplitudes are totally going to be vanish. Then the system is stable only, absolutely stable. Next, fourth system I am going to discuss about is like this. That is, f of s is equal to 1 by s. Then s is equal to 0. The pole is lying on exactly at the origin. Then it is known as marginally stable or critically stable system. Marginally stable or critically stable system, and its impulse response will be like this, constant. Next, if I consider the system f of s is equal to 1 by s square plus a square. Okay, 1 by s square plus a square. Then the poles are lying on plus or minus ja on the imaginary axis. If the poles are lying on the imaginary axis means they are marginally stable, like this. Above marginally stable or critically stable system, and this is its impulse response, 1 by s square plus a square, or a by s square plus a square. It is nothing but it is its Laplace transformation. Its impulse response will be in terms of sinusoidals, either sine or a cos. So sine or cos signals are having the amplitudes in between plus or minus 1, constant amplitudes. Okay, that's why it is known as a marginally stable system or critically stable system. Next, I am having f of s is equals to 1 by s square. Then its roots are lying on two roots lying on origin. If two roots are present at the imaginary axis, two same roots or repeated roots are existing on the imaginary axis means the system is unstable. 1 by s square is nothing but ramp signal. For the unit step signal it is s. For t, Laplace transformation of t is nothing but 1 by s power n plus 1. N is nothing but power here, 1. 1 plus 1 is nothing but 2. 1 by s square is nothing but its impulse response is nothing but ramp signal. Ramp is nothing but it is continuously increasing. As time t tends to infinity, its amplitude is also infinity. So it is unstable. And next, I am going to discuss about the system 1 by s square plus a square whole square. Then roots will present. Total how many roots? S square whole square. Total 4 roots. And these 4 roots are repeated roots on imaginary axis. I already told you that if the roots are repeated on the imaginary axis, then the system is unstable. And what is its impulse response? It is continuously increasing amplitude sinusoidal signal. If it is continuously increasing, at time t is equal to infinity, it is having infinity amplitude. It is not a bounded output. So the system is unstable. And next system 1 by s minus a. S minus a equal to 0 means s is equal to a. Means the root is lying at plus a. If the roots are lying on right half of the s plane, this is actually j omega, this is s. This is right half of the s plane, left half of the s plane. If the roots are lying on the right half of the s plane, then the system is unstable. So it's e power at, its impulse response. E power at means it is continuously increasing. Next, f of s is equal to 1 by s minus a whole square. Two roots are present on right side. If single root is present on the right hand side, then the system is stable. I am having a system in that the system is of order 4, means 4 roots are available. Out of 4 roots, 3 are lying on the left hand side and 1 is lying on the right hand side. Means blindly I can say that the system is unstable. And it is t into e power at. So like this I will get the impulse response. Okay, so this is about the introduction of stability. Next, in the next class, we'll see Ruth Hurwitz's criteria. Thank you.